Welcome students. Now in this video we are going to talk about the tool failure and the tool life. Okay. So let us talk about the tool failure first and then we'll talk about the tool life. So what is tool failure, or when can you say that the given tool is failed? So see, whenever the tool is not performing satisfactorily, okay, then we can say that the tool is failed. And for that we are having the online parameters which can decide the satisfaction of machining. So which are these online parameters that we are going to check for whether the tool is okay or it is failed? So number one, we are having the surface finish, the produced surface finish on the workpiece. Second, we are having the cutting forces in the operation, cutting forces. So these are all online parameters. Third, we are having the power consumption, Fourth, we are having the temperature induced in the cutting zone. So these are the online parameters. Based on that we can decide whether the machining is okay with the tool or not, or given tool is failed. So see, when we talk about the surface finish, okay, so you started the work. At the beginning of the operation you are getting very good, excellent surface finish on the component, okay, but after some time passes, if you are observing certain tool feed marks, some lines on the workpiece, then yes, you can say that the tool is failed. Okay, so the first parameter that you can have online kind of inspection, you are having whatever the produced surface finish on the workpiece. Okay, now see, second, the cutting forces. So see, cutting forces we can simply measure by putting the dynamometer below the table, okay, and we are having some calculated value for the cutting forces, isn't it? And during the machining, if you measure this value of the cutting forces which are induced in the operation, cutting operation, and you observe that the values that you are getting by this dynamometer are 15% more than the actual values that we have calculated. They are more than 15% of the actual values that we have calculated, and what we are getting onto the dynamometer, then you can say that yes, the cutting forces are goes beyond the limit and the tool has failed. That is what, when you measure this value of cutting forces by the dynamometers, if they are exceeding the limit of 15% than the calculated forces, okay, or 15% more, rather I can say 15% more than the calculated values, then you can see that the tool is failed. Same thing about the power consumption. See, so if you put the ammeter at the input of the electrical motor for the calculation of power, you can measure the current drawn by the motor, isn't it? So at the input terminal, if you provide the ammeter to measure the how much current that motor is taking, so if you observe that if the current drawn by this motor, electrical motor, is more than the 15% of the calculated, then you can say that of course the motor is taking more amount of current, then definitely it is going to increase the power consumption. So when this current drawn by this electrical motor is more than this I current drawn by the electrical motor more than 15%, you can say that the power consumption goes on increasing. So you can get the idea that the tool is failed. Okay, now if you talk about the temperature induced in the metal cutting zone, so when you can see in normal machining, when it is going on, so no any gases you can or fumes you can observe into the metal cutting zone. And also by looking to the color of the chip, we can predict whatever there is increase in temperature or not. Generally, see, if you look at the color of the chip which is produced during the normal machining, is generally bluish or metallic color. But see, whenever there is a temperature rise, this chip is going to be blackish in color. And sometimes also you can observe some fumes or gases are coming out from the metal cutting zone. At that time, you can definitely say that the temperature in the metal cutting zone has increased, and you can predict or decide that the given tool has failed. So in this way, by having these online measuring parameters, okay, you can able to decide whether the given tool is failed or not. Now if you look at what are the modes of tool failure, so basically there are three modes of tool failure. One is the failure of the tool because of plastic deformation. Second is failure of the tool because of mechanical breakage. And third thing or third mode we are having the failure of the tool naturally or gradually, that is gradual wear is responsible for the tool failure. Let us see that. Let us see the modes of tool failure. So as we discussed, what are the modes? Number one, the failure of the tool, the failure due to the plastic deformation. Second, the failure due to mechanical breakage. And third is failure due to gradual wear. Okay, so these are the three modes of tool failure we are going to discuss here. So of course, see, what is this failure due to the plastic deformation? So see, we already discussed that the tool is having one very important property, that is the hot hardness temperature. Okay, when the hot hardness temperature of the tool and the induced temperature in the metal cutting zone, in between these two, the induced temperature goes beyond the hot hardness temperature of the tool material. Okay, so definitely what will happen at that temperature? Tool will lose its properties, very important mechanical properties, that is the strength and hardness, and the tip of the tool will deform plastically. So what I am saying, so when the temperature which is induced in the metal cutting zone, temperature in the metal cutting zone goes beyond what? Goes beyond the hot hardness temperature, the hot hardness temperature of the tool. So definitely tool going to lose its strength and hardness, and if you see, this tip of the tool will simply deform plastically and the tool failure will occur. Okay, so this is a plastic deformation of the tip of the tool, and we can say the tool is failed. So this is the first mode of tool failure, that is the failure of the tool due to the plastic deformation. Now see, now if you look at this failure of the tool because of plastic deformation, so whether it is the abnormal failure or the normal failure. Okay, so of course this is the abnormal failure, because see why this is happened. That is the first thing, is that we have chosen a wrong tool. because if you are having this much temperature going to induce in the metal cutting zone, you should select the tool with the higher hot hardness temperature. So that is again because of the wrong selection of the tool material. That is the first reason. And the second reason is that there is a wrong selection of process parameters like speed, P, depth of cut. We have select wrongly. That is why the temperature of the metal cutting zone goes at very high or beyond the hot hardness temperature. So of course, if we talk about this kind of tool failure because of say plastic deformation, so this is not the normal failure. This is not the normal failure. This is the abnormal failure. Please remember this. Now let us talk about the second mode of tool failure, that is failure due to the mechanical breakage. Okay. Now see, when you are having this workpiece material like this, say this is your workpiece material and the tool is now going to machine this surface of this workpiece, isn't it? Now see, if in this tool material any void or any hard inclusion or any say big blowhole or any which is hard inclusion, if it is present into the tool, so what is going to happen? So say when tool is start its operation, okay, and whenever there will be this blowhole or the sand inclusion come in front of the tip of the tool, what will happen? There will be the sudden impact loads are going to act on the tip of the tool and the tip of the tool is break away or get broken, isn't it? So because of this any blowhole or because of any hard inclusion which is present inside the workpiece material, there resulted into the failure of the tool, breaking up of the tool, isn't it? So this kind of tool failure is due to the mechanical breakage. It is kind of say tool tip is cut away, break away from the tool. So this is the failure of the tool due to mechanical breakage. And again, if you want to differentiate or want to decide whether it is a normal failure or the abnormal failure, so of course here there is no any mistake by the tool, it is doing its operation. So because of see wrong quality or wrong material is coming onto the machine, so this is happened. So again this is the abnormal failure, this is not the normal failure of the tool. Very important, please remember this. So again the failure of the tool because of this mechanical breakage is also the abnormal failure. Okay, and the third kind of the mode of tool failure we are going to see is that the failure due to the gradual wear of the tool. Gradual wear, the failure due to the third thing, these are the gradual wear. Okay, so if you look at this gradual wear, that is gradual means tool, we have selected the tool, we put the tool on the machine, we work with that tool, we get the material removal, we get the number of pieces, and after some time of course its wear and tear takes place and the tool is failed. So this is the gradual wear. This is a normal wear, is a normal failure of the tool. See, this gradual wear is differentiated or classified into two kinds of wears. One is the crater wear and the another is flank wear. So the wear which is taking place at the rake portion of the tool or rake face of the tool, it is the crater wear, and which is produced or present at the flank portion of the tool, it is known as the flank wear. So let us draw the diagram so that you can able to understand. So this is our tool. Okay, so see the chip is continuously moving on the rake face of the tool. So because of that, see the chip is always in contact with the tool, rake face of the tool, and see from the tip of the tool to at certain distance we can see some spherical depression which is present on the rake face of the tool. Because of this, see the constant movement of the chip over this rake face. So because of the friction and because of this wear and tear, high temperatures, this wear will be present on the rake face of the tool from certain distance from the tip of the tool. This is tip of the tool. It is not directly starting from the tip of the tool but at certain distance. So this wear is our crater wear. And if you look at the flank portion of the tool, we are getting this wear. It is known as the flank wear. Of course, this wear is because of the frictional wear and tear between the workpiece and the tool. Because of that, we are getting this kind of depression here, which is nothing but the flank wear. Okay, so I hope the wear, crater wear कहाँ पे होती है? On the rake face of the tool from certain distance from the tip of the tool. This is the crater wear, and at the flank portion we are getting the flank wear. Now if you look at the reasons, main reasons for the crater wear and the flank wear. So let us talk about the crater wear first. So see, so the main reason for having this crater wear is nothing but the abrasive action of the microchips which are present at the interface of this chip and the rake face of the tool. Okay, so crater wear, the first important reason we can have the abrasive action of the microchips which is present at the interface of this tool and chip. It will cause the wear of this tool. Second, we can have the abrasive action of the fragments of the built-up edges which are coming in between the chip and this tool rake face. So because of that also we are getting this maximum wear and tear of the tool and the crater wear is happening. So one is the abrasive action abrasion of microchips. Second is the abrasion of the fragments of built-up edges. We discussed about the built-up edges. And third thing is that the maximum or predominant, we can say, the phenomena of this crater wear is the diffusion wear. Okay, so diffusion is what? As we know that the temperature in the metal cutting zone is quite very high. Okay, and you know that the diffusion is temperature dependent phenomena. So here at higher temperature, what happened? The tool material or tool atoms are going to diffuse from the tool body onto the workpiece material. Okay, so when it is coming out, they are making a kind of edge or layer onto this body of the or rake face of the tool, which will get wear and because of that, when the material is coming out or this tool material is diffusing onto this workpiece and creating the layer, so what happened? There is a loss of tool material only, isn't it? So diffusion is one of the very important phenomena to have this crater wear. At higher temperature, the atoms from the tool material are diffused onto the workpiece material, and when the tool material atoms are diffusing means there is a loss of tool material. So definitely this is contributing for the crater wear. Okay, so generally see, if you take the example of the ferrous material, and in ferrous material if you use the diamond as a tool material, so ferrous, iron is there, in diamond the major constant element is carbon. So carbon is having huge affinity towards the iron, so definitely iron get attracted by, or carbon from the diamond is diffused from the diamond tool and making the edge. Okay, that is a loss of the diamond tool. So that's why diamond tool is not basically used for the machining of the ferrous materials, because of this diffusion. Because of the diffusion, there is a wear of the tool, isn't it? So that is, the diffusion is the predominant phenomena in this crater wear. Now see, another important thing is that what I told you that this crater wear will start from certain distance from the tip of the tool. So what happens, see, when the chip is going to, or when the force is applied by the tip of the tool into the layer of the material, okay, so the upward force is acting on the layer of the material, and see, if this is the workpiece, so this chip is getting lifted upwards because of this upward force which is given by the tip of the tool. It will get lifted upwards, and because of, after some time, because of its self weight, okay, because of its self weight, it is going to fall down onto the rake face of the tool, isn't it? And this is happening continuously, that is, whenever the tool is penetrating into the workpiece, it's constantly lifting the chip up, and because of self weight it is falling down. So see, there is a continuous contact, and of course tool is given with the feed F, so tip is always moving ahead, and this chip is always lifting up and striking back onto the rake face at particular or from certain distance from the tip of the tool. And because of that, see, lot of friction at this chip and this rake face. Because of that, there is a high temperature, and because of this higher temperature, the tool is going to lose some properties, isn't it? And that is why the wear and tear is very fast there, and this will result into the some spherical depression or crater you are getting here at the certain distance from the tip of the tool. Okay, so this is because of higher temperature. Actually, this is because of higher temperature. And why this higher temperature is there? So because of this reason, isn't it? So that is the reason why the crater wear is always at certain distance from the tip of the tool. So this is about the crater wear. Now if you look at the flank wear, so again, of course, there is a wear and tear between the tool and the workpiece. The main thing, the main phenomena or predominant phenomena here is the adhesion between the workpiece material onto the tool, or tool materials onto the workpiece. Adhesion is what? Adhering or welding of the microchips or fine chips at very high temperatures. Okay, and say when these are get welded or adhere, again, because of again the friction between the workpiece and the tool, they are simply removed. But when they are removing, some little bit quantity of the tool material also coming with that, then it is also producing some or having some loss onto the tool material and resulting into the wear. So actually in flank wear, of course, flank wear, the abrasion between the tip, between the chip and the tool, abrasive particles, that is action of the abrasive particles, microchips. Then again the action of the fragments of the built edges, they are also present there. And third thing, very predominant, as in crater wear diffusion is predominant, in flank wear the adhesion is predominant. Because of that adhesion, these microchips are going to adhere to the surface of the tool on the flank surface, and because of the friction between the work and tool, these chips, they are not permanent joint, so they are get removed. But along with this adhered chip, microchips, some tool materials also having also they are moving with the that chip, that adhered chip, and producing loss to the tool material. So this is the flank wear. Okay, so in this way we have discussed about the modes of tool failure. In that, failure because of the plastic deformation, failure because of the mechanical breakage, and the gradual wear, failure because of gradual wear. In that we are having two wears: the wear which is present on the rake face of the tool, that is the crater wear, and at the flank portion of the tool, it is the flank wear. And the reasons or sources of the wear we have discussed. So after looking the modes of tool failure, now we are going to talk about the tool life. The tool life. So what is tool life? So tool life is nothing but it is the time, or it is the actual time between the two successive regrindings during the machining. It is known as the tool life. That is the actual time between two successive regrindings is nothing but our tool life. So how this tool life is measured? Say the tool life can be measured. The most common method or way, most commonly we are measuring this tool life, say T, in terms of minute or minutes. Okay, this tool life in most common way it is measured in terms of the minute. Or suppose you are having the mass production onto the floor, then in case of this mass production we can measure this tool life in terms of the number of pieces produced by the tool between two successive regrinds. You can define like that for the mass production. If there is mass production, so yes, of course we are more interested in the numbers. So between the two successive regrinds, how many parts or how many numbers of workpiece got machined by the tool is nothing but the tool life, we can say. Or sometimes this is also measured in terms of the volume of material removed. Between two successive regrinds, that can be the way of the measuring of tool life. Again, one more way we are having, that is based on what surface finish we are getting in the cutting operation between these two successive regrinds. So produced surface finish can also be the one of the way for the prediction of the tool life. Okay, so this is how we can able to represent the tool life. Okay, so see here, basically the scientist or the researcher F.W. Taylor, कौन था? F.W. Taylor, in the last of the 19th century or in the beginning of the 20th century, so he published his work in 1907 में in the transactions in ASME. In that he published around 300 pages of his work, and he was mostly interested in the empirical research in this metal cutting. So around he worked for 30 years and his work get published in 1907 in the transaction of ASME, where he published his work around 300 pages. And this scientist, this F.W. Taylor, he gives one relationship for the tool life. Okay, so that definitely we are going to see. But before that, what we are going to see, the factors which are going to affect the tool life. That is very important. The factors which are going to affect the tool life. So which are these factors that we first discuss, then we'll go for that Taylor tool life equation. So here, which are the factors? Factors affecting tool life. So number one, we are having the properties of workpiece material. Of course, very easy. That is, when we are having the hard workpiece material to machine, then definitely we have to use the harder tool material, and of course when the workpiece is hard, the wear and tear of the tool is definitely higher amount. So tool life that we are going to get in this machining is definitely less. On the other hand, suppose the given workpiece for the machining is very soft and ductile, so definitely we are getting the maximum tool life, isn't it? So in this way we can able to correlate with the workpiece material the tool life. But see, there is no any quantitative relationship exist between the properties of the material, work material, and the tool. That is why just we can say only like this: when the workpiece is hard, we can have the minimum tool life, and workpiece is soft, we can get the maximum tool life, like that. Second parameter that we are having, the tool geometry. Tool geometry. See, this is also we have learned that when we are having the rake angles, the back rake angles, where this angle goes on increasing, the cutting forces are going to come down. The forces or the cutting forces going to come down. So definitely in that case, what is going to happen when the rake angle is increases? We have also seen that wear length increases. So tool life goes on increasing when the rake angle increases. Even when we increase these relief angles when we are increasing, then also we can have the increase in tool life that we have seen, isn't it? So this is how the tool geometry is also affecting the tool life. But again, there is no any quantitative relationship amongst the tool geometry and tool life. We can have only this empirical relationships or experimental observations for us, with us. Okay, now the third thing, we also seen that use of the cutting fluids decreases the cutting forces up to 25 to 30%. Okay, so definitely when the cutting forces are goes on decreasing, there is increase in the tool life. So use of cutting fluids decreases the cutting force by 25% to 30%. This is ultimately what it is going to decrease the forces, and ultimately it is going to increase the tool life, isn't it? And the fourth thing, after this use of cutting fluids, we are having the process parameters. Which are the process parameters in the machining? We are having speed, feed, and depth of cut. Okay, speed, feed, and depth of cut. And see, in this fourth point, that is process parameters, the F.W. Taylor in 1907, that he proposed the relationship between the cutting velocity and the tool life as, say, V t to the power n is equal to constant. V t to the power n is equal to constant, where V is the cutting velocity, T is a tool life, and C is a constant. So see here, V is what? The cutting speed or cutting velocity, which is in meter per minute. T is a tool life, which is in minute, and N is Taylor's exponent, which values are depend upon the material that you are using as a tool material. Okay, say if you are using the high carbon steel tools, say if you are using, say, N is a Taylor's exponent, this N is equal to 0.05 to 0.1, we are having the high carbon steel tools. This is equal to 0.1 to 0.2 when you are using high speed steel tools. This N is equal to 0.2 to 0.4 when you are using the carbides as a tool material. When you are using the ceramics, this value will be from 0.4 2.6 for the ceramics, and this value will be for N from 0.7 to 0.9 when you are using the tool material like diamond or the cubic boron nitride. Okay, so this is the value of Taylor's exponent N. Okay, and what is C? This is the constant. That is, this will measure the cutting velocity for 1 minute of tool life. Okay, so this is the equation, very famous equation, Vt to the power N is equal to constant. Again, we are having the generalized or modified. We are also having the modified equation, modified Taylor's equation or modified Taylor's tool life equation is what? When we have to again correlate the feed and depth of cut in this equation. So we are having V T to the power N, feed to the power P, and depth of cut to the power Q is equal to constant. So this is the modified or generalized tool life equation. Okay, where this P and Q of course less than 1 and P is greater than Q. Okay, where F is what? This is the feed and this is the depth of cut. So this is the generalized tool life equation. Now if you plot this equation on the curve, that is, see, here is the velocity versus the tool life in minute. It is in meter per minute. What you will get? You will get this hyperbola, isn't it? So see here, as the tool life, you want the maximum tool life, then definitely you have to decrease the speed, isn't it? But see, decrease in speed is not the solution, because when you are decreasing the speed, definitely material removal rate is coming down, and when the material removal rate is coming down, your production rate is coming down, isn't it? So directly it is affecting your production rate. Or you have to see, you have to select, if you want the less, if you want to have maximum production rate, so definitely when it is possible, when you are using the very high cutting speeds. But at very high cutting speed, what is happening here? You are getting a very less tool life. So see, even though we are having these three process parameters like speed, feed and depth of cut, the most highest influence amongst these all is of cutting speed. Cutting speed is very, very important when we talk about the tool life. So that is why the thing is that here we have to choose the optimum. We have to balance this thing, isn't it? We want definitely we want the production rate as well as we want the good tool life. So some balance should be there, and that is why the selection of optimum cutting speed is very, very important in the machining. Okay. Now suppose if you log this, if you plot this curve on log paper, how it will look like? This is log V log T. You will get this equation or these straight lines. Okay, so this is what, say this is for tool A and this is for tool B. So here what you can see, these A and B tools having these parallel lines having the equal slopes, isn't it? Slope is same only. So what does it mean? That actually the B is having higher value of intercept on the axis, so definitely the constant C for the tool B is larger or higher than the constant for tool A. Okay.